Hello, everyone. Today, Shahla Nasserasr from Rochester Institute of Technology will tell us about multiplicities of eigenvalues in symmetric graph matrices with 0 entries for non-AGs. Shahla?
Thank you. Thanks for inviting me. This is about the multiplicities of the eigenvalues, symmetric matrices representing the graphs. And my goal is to show you some of the progress that has been made on the multiplicities in this area. The main results in this talk are from joint works with two groups, both of them AIM groups. The first one was with Ferrara, Flagg, Hall, Hartman, Lind, Mayer, and Shader. And the second one, which is the most recent one, is with Favret, Hall, Lehman, Mayer, Oblak, and Ishmaeluk. So first of all, let's see the matrices that we are going to consider here. So those are symmetric matrices when they're for a given graph, when their ij entry is going to be non-zero whenever there's an edge from I to j, and 0 whenever there is no edge, and the diagonal entries are going to be any possible value. We don't have restrictions on them. And all these matrices are going to be in a set called S of G. And given that, the question, which is the main question here, the inverse eigenvalue problem, is what are the eigenvalues of matrices in S of G? And as you can imagine, this is a difficult question because it's asking for the eigenvalues of infinitely many matrices in one set. And it has been studied very well. There are lots of really nice techniques and really nice results. But at the same time, there are many, many open problems. So one way to think about it is that, okay, instead of the values of the eigenvalues, can we answer questions about the multiplicities of eigenvalues? So, such as what are all possible multiplicities of the eigenvalues and so on. One thing that I need to mention is that these are symmetric matrices, therefore the algebraic multiplicities and geometric multiplicities are all the same. So having that, we define this set called L of G, L for list, which is the list of all possible sequences of positive integers, so that those integers are the multiplicities of the eigenvalues of the matrix in S of G. And here I'm using some notations. So sigma of A means the spectrum of A, and then lambda 1 to the parentheses M1 means lambda 1 is repeated M1 times. So M1 is a multiplicity of lambda 1. So the multiplicity questions can be studied in two ways. One is to order the eigenvalues and then ask for the multiplicities. That is called the ordered multiplicity list. And another is to not order the eigenvalues, but list these positive integers as an ordered list of numbers. And that's called unordered multiplicity list. And here we are only going to consider the unordered multiplicity list. So one big question here is, for a given graph G, find L of G. And we can think about L of G, finding L of G as the sub-problem of the inverse eigenvalue problem. But also, if you add an addition question, meaning if a multiplicity list is achieved by a set of eigenvalues for a matrix, then what are the conditions on the eigenvalues to be, with those corresponding multiplicities, to be the spectrum of a matrix in S of G? Then if you can answer that question, then we have basically answered the inverse eigenvalue problem. So it is a sub-problem, but it's also a different way of studying the same problem. And if it turns out that there are no restrictions on the eigenvalues for a given multiplicity list to be the spectrum of matrix in S of G, then we call that multiplicity list to be spectrally arbitrary. So for instance, a very small example in path on 4 vertices, it is well known, this is true in general, but I'll mention in a minute, that any set of 4 distinct values can be the spectrum of a tridiagonal matrix of size 4, a symmetric tridiagonal matrix of size 4. Therefore, a sequence of ones, 1, 1, 1, 1, is spectrally arbitrary for people. So our question here is not only just determine L of G, but also find the multiplicity lists in L of G that are spectrally arbitrary. And starting from the simplest possible case, paths. This has been answered a long time ago in 3 different papers, I believe. 1960, 67, and 69, that for any path, let me mention it differently, for any set of distinct n values, there is a symmetric tridiagonal matrix, which those values are its eigenvalues. And moreover, any symmetric tridiagonal matrix can have only distinct eigenvalues. Therefore, the list of Pn, path on n vertices, is exactly the sequence of ones and nothing else. And moreover, those are spectrally arbitrary. So the one way to see this one direction, the proof of this is quite easy, which I've shown it in the picture. So we want to say that if you have a symmetric tridiagonal matrix when the diagonal entries above and below, when the entries above and below the diagonal entries are not zero, then it can only have simple eigenvalues. And the reason for that is that if we delete the red row and column, the first column and the last row, what we get is a low triangular matrix with non-zeros on the diagonal entries. Therefore, that's an invertible submatrix of the original matrix with size n-1, which means the rank of the larger matrix cannot be less than n-1. So the eigenvalues are, this is about the nullity, but because the diagonal entry is not free, the statement can be said for any eigenvalue. So the eigenvalues are all simple, and it's shown that for any set of distinct eigenvalues, there is a symmetric matrix with those eigenvalues. So that means the inverse eigenvalue problem for paths is completely solved. Now, having this sequence of ones, we could ask the question for what the sequence of ones for any graph, and that is it achievable for any graph? The answer is yes, and in fact, it's spectrally arbitrary too. That has been shown by Monford and Shader in 2013, when they showed that if you start with a square matrix and let the diagonal entries to be these distinct values and put everything else to be zero, then because these are distinct, using the implicit function theorem, there's always going to be an open interval for the values that we want, so that we perturb this matrix in any way that we want to get a symmetric matrix with the eigenvalues of lambda 1 to lambda. So that sequence of ones is spectrally arbitrary for all graphs. Okay. So which graphs do we know that their L of G is completely determined? So there's quite a few lists, but not many. I've listed some in here. So paths we just saw, and then double paths when there are two paths, two of the internal vertices are connected by an edge. In linear trees, when the vertices of degree at least 3 are all on one path, and also stars, generalized stars, and double generalized stars. Those are completely, the inverse eigenvalue problem is completely solved for. These are all trees. There are some non-trees also that we know the answer for them. So for instance, the complete graphs means a matching. And then these two graphs, when we have a complete graph with a pendant path hanging from it, or two complete graphs with a path joining the two together. So again, the inverse eigenvalue problem for these is completely solved, therefore L of G is also completely known for. So finding L of G for a given graph G can be quite difficult. So we can reduce the question to, can we find some individual multiplicity lists, which also can be difficult. I'll talk about that in a minute. But we can also reduce the question even further and say, can we give partial information about the multiplicity lists of graphs? And in the case of trees, we know some answers, such as it's known that if lambda 1 to lambda q are the eigenvalues of a matrix corresponding to a tree, then the smallest and largest eigenvalue must be simple. And the proof for this is quite nice, so I've highlighted it here. It just uses the fact that because this is a tree, we can take a diagonal matrix with diagonal entries d1 to dn being either 1 or minus 1, and construct this the matrix DAD inverse so that its off diagonal entries are all non-negative. And now because of the freedom of diagonal entries, we can also shift them so that they become non-negative as well. or positive even. And now we can use that for Frobenius theorem to say the largest eigenvalue has to be simple. But all of these are also applying for the negative of whatever we did. Therefore, the smallest and largest eigenvalues must be simple for any tree. So that's one piece of information that we have in the case of trees. But going back to the paths, if you remember that picture that I had for the matrix with deleting the red column and row, the paths give us this large full rank submatrix. So we can ask this question that do these help in saying something about the nullity of trees in general and not just paths? And that has been answered with this nice lemma that says if we have a pattern vertices in the set alpha, then by deleting all of the vertices, the nullity of the matrix, the new matrix, is not going to go down by more than one. And again, the proof for this is quite nice, so I'll mention that quickly too. So if you remember in the definition of the set S of G, we didn't mention anything about the labeling of the vertices. And that's because we are only concerned about the eigenvalues, and the eigenvalues are preserved under permutation similarity. So we don't care about the labeling, but labeling sometimes is extremely helpful in some of the proofs, and this is one instance of that. So the way that we label the trees here is that we start with the vertices of the path and label them so that we get that tridiagonal matrix. So those are the 1-1 block of the matrix A. And then, moreover, we label the rest of the tree so that this Y transpose, the 2-1 block, is in echelon form. So that means the non-zero entry in row I is to the left of the non-zero entries to the rows below it. So having that, we will do the exact same thing that we did for the path, meaning delete the first column of this matrix and the row that corresponds to the last row of the path, so meaning the last row of the 1-1 block, to obtain this new matrix called A alpha 1. The parentheses mean delete the row alpha column 1. That's supposed to be L, not 1. And what we get, just similar to the paths, is that the matrix B is a lower triangular matrix, which is invertible. So that means now we can perform the Schur complement. But the good thing about our labeling is that when we do the Schur complement, the blocks that we had here, the components that we obtained from deleting the path, are not going to be affected. So that means in this Schur complement, all of these diagonal blocks are exactly the same as before. Everything above is 0. The things below might change, but that doesn't change the eigenvalues or the nullity of the matrix. So, so what that means is that the algebraic multiplicity of the eigenvalue 0 in this new Schur complement matrix is exactly the nullity of the diagonal blocks, and those are same as before. So we get this nice nullity of the A deleted all of alpha is at least the nullity of original matrix lengths. So deleting one whole path doesn't drop the nullity by more than 1. And here I've tried to highlight that proof in this example. So the original matrix is the left one. We delete the red ones. We obtain this right matrix in here. And as you see, after the Schur complement, the blocks that I have, the kind of green blocks, do not change. And that's exactly why our nullity stays the same as the Schur complement. So having that, we deleted one vertex and we realized that the nullity doesn't go down by much. So what about we delete more vertices? And it turns out that if we delete more this path, the vertex disjoint paths, then the nullity of the, we cannot actually mention in terms of the multiplicity of the eigenvalue, and the multiplicity of an eigenvalue of the matrix in the new matrix when we delete all of the vertices of the paths is going to be at least the maximum of these two values, the maximum between the multiplicity of the lambda in the original matrix minus the number of paths and 0. Okay, so how is this even useful in finding some information about the eigenvalues? It is quite useful in a lot of cases. One of them is a simple example. So if you look at this tree called Rayleigh-Fowler tree, which by the way, it turns out that this is more like the Peterson graph in the inverse eigenvalue problem. Using previous inequality, we can show that this a matrix for this, any matrix for this, cannot have two eigenvalues both with multiplicities 3. And one way to see that is that, let's say there is such a matrix. So let's say there are two eigenvalues for matrix A, lambda and mu, such that both of them have multiplicity 3. If we delete the colored paths, the green and red ones, we are ending up with vertices 6 and 9. So that means in that submatrix, we are going to have multiplicity of lambda to be at least 1 because of this inequality that we just proved. But what that means is that the two vertices, 6 and 9, because the submatrix induced by them is just a 2 by 2 diagonal, so that means those two vertices must be labeled one with lambda, one with mu. And there's nothing special about 6 and 9. We can delete different vertices and get the same statement about any two pendant vertices of far enough distance. But then there are too many of them, so we can't fit mu and lambda on all of them. And that means we can't have two eigenvalues of the same multiplicity of 3 in one matrix. So that's one piece of information that we learned from that inequality. But in fact, we learn a lot more than that. So this is another example. For that, we need the definition of path cover number. So path cover is simply a set of disjoint paths that cover all of the vertices of the graph. And path cover number is the minimum cardinality of such paths. So the minimum number of paths that cover all of the vertices. And it's noted by a capital P of the graph. And then we also have the maximum nullity or maximum multiplicity, which is the maximum multiplicity among all eigenvalues of matrices and such. Now, if you go back to that previous inequality that we just showed, the multiplicity of lambda in the matrix, when we delete all of the disjoint paths, is at least this maximum value. If we delete the path cover, that means we've deleted all of the vertices of the graph, so nothing is left. So that means this left hand, the right-hand side of, left-hand side of the inequality is 0. And in the right side, we have this maximum multiplicity of lambda in A minus K of 0. So what that means is simply that the path cover number is at least maximum multiplicity for all of the trees. And in fact, it is shown that maximum multiplicity and path cover are exactly the same for trees, but that inequality is only to prove one of the directions. So I've shown you some of the applications of that inequality. That is, by deleting vertex joint paths, the nullity goes down by the number of paths, if it does. And the next question that we could ask is that, what about graphs in general? Can we say similar statements for non-trees? So for that, I need to give you some definitions. We use these words in the paper. So linkage is simply the union of disjoint paths. And the order of linkage is the number of paths. When we say alpha beta linkage, that means the set of paths when they start from the set alpha and end at the set beta. So alpha is one set of endpoints, beta is another set of endpoints. And the unique linkage means that if we fix the endpoints, then there's only one such linkage between them. And then alpha beta rigid linkage means that if we fix the endpoints as sets, not the individuals anymore, then there's only one alpha beta linkage between them. So by this definition, uniqueness doesn't imply rigidness, but rigidness does imply uniqueness. And having that, we've shown in that paper in 2019 that if we delete all of the vertices of a linkage, which is rigid, then the nullity is not going to go down by more than the number of elements of the linkage, so the number of paths in that linkage. So note that this is true for all graphs, not just the trees. And again, we are going to use this to say something about the structure of the matrices that are restricted from the multiplicities. So one thing that I need to mention is that this statement was again for nullity, but because our the eigenvalue entries are all free. If the statement is true about the nullity, we can always shift with any value that we want to make the statement about the multiplicity as well. So the same statement is true when lambda is an eigenvalue of A, then the multiplicity of lambda in the matrix obtained by deleting all the vertices of the linkage, the rigid linkage, is going to be at least the multiplicity of lambda in A minus the number of paths in the linkage. So how do we use that to give more information about the structure of the graph and eigenvalues given some multiplicities? So I'll start with this one, that again, Borelli palette tree, counterexample for spectral arbitrariness. So Shahla and Borelli showed in 2004 that if you have this matrix with multiplicity with the spectrum lambda 1 to lambda 5, so 5 eigenvalues, where their multiplicities are 1, 2, 4, 2, 1 in that order, then the eigenvalues have no choice but to satisfy this relationship. So the sum of the lambda 2 and lambda 4 must be the same as the sum of the lambda 1 and lambda 5. And that means that this multiplicity list is not spectrally arbitrary. So what we did in this paper is to generalize this statement, given infinitely many trees that are not spectrally arbitrary. So if you look at this matrix, this graph one more time, it's K1 tree with 2 pendant vertices hanging from each of the leaves of K1 tree. We do the same thing, except that from K1 tree, we hang pairs of vertices, K pairs from each of the leaves. And so we call that to be TK. So what we showed in that paper is that if we take a matrix for this graph, which has this spectrum, so lambda 1 with multiplicity 3k plus 2, lambda 2 with multiplicity 3k minus 2, and so on, then the eigenvalues have no choice but to satisfy this linear equation. So again, that means that multiplicity list on the top is not spectrally arbitrary trees, and it gives finitely many trees with a multiplicity list that is not spectrally arbitrary. So I'm actually going to show you the proof of this because it's quite fun, but also I will use it later in the new paper. So how does that work? Well, we are going to delete paths in different ways to give information about the entries of the matrix as well as eigenvalues. So for now, let's just delete that blue and red paths, P7 and P5. So I'm considering here T3. So that means 3 P3s are hanging from each of the pendant vertices of K1 tree. So we are deleting those blue and red vertices to obtain 5 paths on 3 vertices and 4 paths on 5 vertices, all of them colored black. And in general, this is T3. If I do that for TK, we will obtain similar thing. If I delete P7 and P5, then we obtain 3K minus 4 P3s and 4 P1s. So going back to our multiplicity equation using the rigid linkages, we said the multiplicity of lambda 1 in B, if I go back to the list, the multiplicity of lambda 1 in B is 3K plus 2. So 3K plus, sorry? Is that the question? I can't hear.
I think not.
Okay.
Can continue.
Should I continue?
Yeah.
Okay. So multiplicity of lambda 1 in B is 3K plus 2. And if we delete 2 paths using that inequality that we have, the multiplicity of lambda 1 with deleting those paths in the matrix with deleting those paths is going to be 3K plus 2 minus, we deleted only 2 paths, so minus 2, which is 2K. So the multiplicity is at least 3K in that submatrix. But at the same time, if you look at what we got here, let me go back to the picture, we obtain a bunch of paths, and we know that the paths can only have simple eigenvalues. Therefore, if I look at the these graphs, I don't know if you saw my mouse. If I look at these graphs that are all paths, then the multiplicity cannot be more than the number of those, because each of them have only simple eigenvalues. So the multiplicity of λ1 in the resulting submatrix is at most 3k as well. So it's exactly 3k. And we have 3k components. So λ1 appears as an eigenvalue of each of those components. Am I clear on this? I see Dr. Garrett has turned on his video. I don't know if you have a question. Okay, so what we showed is that λ1 is an eigenvalue of each of these components. But let's go back to the picture. Those components are some isolated vertices and some paths of length 3 only. If λ1 is an eigenvalue of those singletons, then that means in the matrix, the diagonal entry corresponding to them must be λ1. Because that principal submatrix, the one by one principal submatrix has λ1 as an eigenvalue. So the diagonal entry has to be λ1. And there's nothing special about these black pendant vertices. I can change the blue and red in a different way to obtain different waves. Therefore, the statement that we make here is true for all of the pendant vertices. So that means every pendant vertex must have λ1 on its diagonal entry. So having that multiplicity forces some of the diagonal entries to be the eigenvalue with the largest multiplicity. Okay, so that's one thing that we learned, but we can play with this in different ways. So we can delete different paths and obtain different information. So here I'm going to delete all the blue paths and 3 vertices together with the pink one. And that gives us only this black vertex, so which is a singleton again. And with the exact same argument, we can show that that singleton vertex must have λ1 on its diagonal entry. But again, there's nothing special about that. We could change the pink and blue in a different way to have that all level 3 vertices must be λ1 in their diagonal entries. So all those diagonal entries are forced to be λ1 as well. But we can even say more by deleting different paths. So in this case, I'm deleting, I'm deleting P5s in all these levels. And what that gives us is that λ1 is already taken for the leaves. Sorry. And the 2 has multiplicity 3k minus 2. And therefore, it has to be, using the inequalities that we had, it has to be the eigenvalue of that root vertex, because that's a singleton, as well as the eigenvalue of all these P3s, the hanging P3s. So the singleton in the root vertex is known as what? Its diagonal entries must be λ2, and the hanging P3 paths must have λ2 as their eigenvalue. Now, if we move to λ3, we can make a similar statement saying that those P3s must have λ3 as their eigenvalues. So if we gather all this information together, what we've learned so far is that the P3s have eigenvalues λ1, λ2, λ3. So the principal submatrix, the hanging P3s, right? Only the black ones in here, all of the hanging ones. So they have 3 vertices, 3 eigenvalues. So the principal submatrix corresponding to them must have a trace as the sum of the eigenvalues. And we also know the other diagonal entries. So we know all of the diagonal entries, which must be for the leaves, which must be λ1, and for the root, it must be λ2. So if we add the trace in that way, we get that trace of the large matrix. The original matrix must be this value. But on the other hand, trace of the matrix is some of the eigenvalues. So if we add the eigenvalues with given their multiplicities, we obtain this. Letting these to be equal, we get this relationship between the eigenvalues. So that multiplicity list of 3k plus 2, 3k minus 2, 3k minus 3, and so on, forces eigenvalues to be in this relationship. And moreover, as you realize, it also forces at least some of the entries of the matrix to be specific values. So that was one of the results in that paper in 2019, and we didn't go further. So at that point, we realized that we gave a family of trees, which for a given multiplicity list and not spectrally arbitrary, and we didn't go further. But later on, we were able to show that in this new paper that there are actually more constraints on those eigenvalues. So for that, we use this branching and collapsing idea that's proved by the branching idea is proved by Johnson and Sayago in 2008. That they showed that if I have a tree like this, that identical branches are hanging from one vertex, and if we collapse all of those to make it just one branch with changing the weights of edges in this way, then the spectrum of the large matrix is simply going to be the spectrum of this small matrix together with k-1 copies of the spectrum of the branch. So if there are k branches, then k-1 copies of it. So that's used for, so we use that as collapsing. So we will start with a large matrix I'll show you in a few minutes, and then we'll collapse as much as possible to get to a smaller matrix that we can find its spectrum in much nicer ways. And in fact, in that paper, we also do the opposite, meaning branching to construct matrices, but I will not talk about that today. So how is that going to work? Well, for that, we need this new definition of independent trees. So before we were deleting vertex joint paths, and we didn't care if they were connected by an edge or not. Here we are looking at independent trees, meaning that they should be far away. That is, there is no two vertices, one from each, that are adjacent. So if they're not, if we have two vertices when no two of them are adjacent, no two of the vertices of the two are adjacent, one from T1, one from T2, then we call them independent. And having that, we have this invertible subtrees lemma that says if we start from a forest and if we pick a matrix A for that forest, so that the mutually independent trees T1 to T, let's say C, have their corresponding principal submatrices to be invertible, then by deleting those, the nullity of the large matrix is at most the path cover of the graph that we obtain by deleting this. I probably didn't say it right again at all, but I'll show an example in a minute. So let me mention it one more time though. So we delete the independent trees, we obtain a graph or a forest. Its path cover is an upper bound for the nullity of the original matrix. So there are some nice consequences of it. For example, we can show that if a matrix has eigenvalue lambda, when its multiplicity is larger than that path cover of the resulting tree after deleting those independent trees, then that lambda has no choice but to be an eigenvalue of at least one of those principal submatrices. So it has to appear as an eigenvalue in one of those. And if you reduce this even further to one tree, you can say that if lambda achieves the maximum multiplicity for a matrix, then when we look at the path cover and obtain some singletons, lambda has to be a diagonal entry for those singletons. Similar to what we did before, but this time we are using the invertible subtrees level. So we will use all of these to give more restrictions on the eigenvalues of the matrix that we just had with the multiplicity. So going back to that example, here we are considering that we have 5 eigenvalues, so not all of them, only 5 of them, with the given multiplicities 11, 7, 6, 2, 2. And by having this, I'll show you that everything is extremely restricted here, basically. So let's see how that works. So first of all, the path cover number of this graph is 11. And I think the colors that I have are exactly 11 paths. So P7, 7 P3s, and 3 P1. And that, using either one of invertible subtrees or the previous paper, we saw that the leaves and the level 3 vertices must have lambda 1, the eigenvalue with the maximum multiplicity on their diagonal matrix. So that means all these green vertices must have lambda on their diagonal matrix. Okay? So keep it in mind. Now, we talked about that collapsing, right? So collapsing said if the branches are exactly the same, we can collapse it, and we know what happens to the eigenvalues. So here the leaves are all identical, so I can collapse those to obtain this graph, and the multiplicity of lambda 1 drops by 9. So that means in this graph, I get this multiplicity, but lambda 1 has multiplicity 2, all the rest are the same. And now I obtain a new graph, which obviously is smaller, and its path cover number is 7. So we will do the same thing, but it's not going to be as straightforward because we need the identical branches. We can't just collapse randomly. So what happens here is that with a path cover number of 7 and eigenvalue lambda 2 with multiplicity 7, I can find paths to say things here, such as if I delete the paths that I have here, if you look at the paths that I have here, not deleting anymore, the blues and the pink ones, that's a minimum path cover because I have 7 of them. And if you look at these pendant P2s, using that invertible subtree lemma, they're independent, and we can see that the lambda 2 must appear as an eigenvalue of those. So lambda 2 must be an eigenvalue of each of the P2s. Again, because of the symmetry, if it's 2 for one of the hanging P2, it's 2 for all of the hanging P2s. So that's a piece of information that we have at this point, that the green P2s must have lambda 2 in them. But we can find a different path cover so that this root becomes a singleton. And that means the highest multiplicity eigenvalue, in this case lambda 2, must be a diagonal tree for this vertex as well. So all the green ones at this point have lambda 2 as their eigenvalues. But that's not enough for collapsing again, because all I know at this point is that these P2s have lambda 2 as their eigenvalues and their leaf as lambda 1 as their diagonal matrix. They could be different matrices. So at this point, we use lambda 3 to force those to be identical, basically. So note that lambda 3, if we take away one of these P2s together with that root vertex, we are, then we are left with a tree with path cover 5, and the multiplicity of lambda 3 was 6 in here. So we have a path cover of 5 and multiplicity 6. So that means lambda 3 now has no choice but to be an eigenvalue of these P2s as well. So at this point, about P2s, the hanging P2s, we know that the leaf vertices have lambda 1s in them, and moreover, the P2s have 2 eigenvalues, lambda 2 and lambda 3. So they're uniquely determined. They have no choice at this point. Everything is known about them. And that means all of them are the same, so we can do the collapsing. So once we do collapsing, we get to this graph, which, as you see, the multiplicities are changing because of that collapsing equation. So what happens here is that we have these P2s hanging, and the path cover is 2. I have 2 eigenvalues with multiplicities 2, lambda 1 and lambda 4. I cannot use lambda 4 because it's already used in the level 3 vertices. So I'm going to use lambda 4 here. And with lambda 4, I can show that it has no choice but to be an eigenvalue of each of these P3s. Therefore, P3s are completely characterized as well in a unique way, and they all are the same. So we can do one more collapsing, and that gives us this matrix. So we started from that large graph, and we ended up this path that almost everything is known about it. Now, what I'm not going to talk about it in this talk is that at this point, we can do branching and go back and construct the matrix if we want. But what we showed here is that the matrix that we have is, in fact, even on its entries, is forced to be unique in a lot of ways. So the entries are forced from the eigenvalues, the multiplicities of the eigenvalues. The eigenvalues are forced, the remaining eigenvalues, and so many things. So another thing that we learned from here is that if I go back to the trace identities that we have, we get these two linear equations with the eigenvalues. So, the linear combination of these two, by the way, will give the exact equation that we had from the previous paper. So not only we get these two linear equations, but also giving some polynomial equations between the eigenvalues, we obtain this cubic relationship between the eigenvalues. So this is the first nonlinear constraint known on the eigenvalues of trees that we found. So what I did here was to show you how restricted the entries and the eigenvalues of a matrix become, given its structure of the graph and given the high multiplicity list. That was just an example, but in fact that's true for a family of graphs called lush hedges. So lush hedge basically is a tree so that all of the leaves have almost the same distance, exactly the same distance from the root, and together with some additional degree conditions. So in that paper, we showed that if a tree is a lush hedge and if a matrix achieves this high multiplicities, then the eigenvalues, the remaining eigenvalues are completely determined with these 5 eigenvalues. The entries of the matrix are completely determined and so on. And that's it.
Thank you for the nice talk, Shahla. Any questions for Shahla? Yes, Monta.
Hello. Am I audible? Yeah, I have a question. Like, is there any connection to this multiplicities with the matching numbers? Because we know the nullity is quite related for the trees with the matching numbers. So can you does there any relation with the matching numbers and this multiplicities things?
I don't know of any.
Okay.
I don't know if anyone else knows here. It's a good question. Yeah, I don't know of any. That's a really good question though.